Good morning. Welcome all of you to this river engineering course, and this is for the third lectures. We are going to talk about the properties of sediment, sediment concentrations variations, and the very interesting topic, the flow structures in natural river systems. This is a combinations of you can look at theoretical aspect as well as the practical aspect of the river engineering. That's what today we'll discuss it. And as I said it earlier, we are going to follow these three books, okay, and starting from the river mechanics, fluvial hydrodynamics, and the stream hydrology. As the last ones is for the introductions for ecologists, you can see that these lectures all will consider all the three aspects of the rivers: mechanics, fluvial hydrodynamics, and the ecological aspects. So looking that, not only that, since it's a higher level courses, we'll also go through its reference journal like Journal of Hydrology, AAC Journal of Hydraulic Engineering, and we can have the Journal of the Sediment Research. The other journals will talk about that. Some of the case studies from the journals also will be discussed in these lectures, and really it will be the interesting lectures to show you the natural river systems as well as these theoretical numerical expressions what we do in a river mechanics. Looking that, let's go for today content what we have. The initially at the first levels I'll show I will introduce you the Brahmaputra rivers, very simple way, at a brief variations of the flow and sediment variations Brahmaputra rivers. That's what I'll discuss first. Then I'll talk about, again I'll repeat it, the fluid sediment mixtures properties, how we can quantify it, because when you talk about the river flow, it's not only water flow, it is water and the sediment mixtures. How to quantify that properties of the fluid sediment mixtures, that what we'll talk about. Again I will come back to the river scales to show it how the flow and suspended sediment concentrations varies it. Then again we'll come back to the, if there is a sediment particles, what will be the terminal velocity of the sediment particles, theoretical as well as combining with experimental things. Then very interesting, so what today we'll talk about the flow durations curve and sediment curve analysis at the river reach scales. Then we'll conclude these lectures. Looking that, let's go for the next slides where I am showing it the reverse survey of the Brahmaputra rivers. If you look at these satellite photographs, the Google Earth availability of the satellite data, the river width at this stretch comes about more than 10 kilometers. So you can understand it, what could be the width of the rivers, 10 kilometers. That's the width of the rivers. Not only that, if you look at this flow variabilities, the discharge, the variability, how much of discharge varies it in these rivers. For a low flow, it starts, it's about 3000 meter cube per second. It's very low flow. During the dry seasons, we'll have the flow which is about 3000 meter cube per second. 1 meter cube as equivalent to 1000 liters. You can understand it, how much of water is flowing it. The average, the flow of these rivers comes about 12,000 meter cube per second. So much variability of flow. Average flow is 12,000 and the low flow is 3000 meter per second, and the maximum flow what is observed it during a 10-year return period flood. That's what comes about 40,000 meter cube per second. So it's a mega river systems. If you look at that, the flow variability starts from 3000 to average 12,000, then it goes to the 40,000. It's how much of sediment it carries it. If you look at that, the average sediment, what in terms of sediment concentrations, if I talk about, it is about 400 milligram per liters average. But as maximum as it can go, it is order of 20,000 milligram for liters. So if you look at this river system, so variability is there in flow, also the sediment. And if you look at the river, the dimensions, it's, as I said, is a 10 kilometer width, and this is about 30 kilometers. And you can see so complex river systems, it's a confluencing, deconfluencing, forming the bars and all. So if you look at this type of river systems and we try to understand the rivers, and we need to have the knowledge on how these sediment laden water flows happens into that, and how mechanics is developed on that, and how far you have a understanding on that. That's what the basic objective of this course, to take it to that levels that we can understand so complex river systems, to how the morphology is changing, how the sediment erosions are happening, depositions are happening. All this process we try to understand it with our basic knowledge of fluvial hydrodynamics. We will talk about more details. So with this, the variabilities, that means what I talk about, that the river doesn't meet its water flow, it's a mixture of the fluid and the sediments. So always there is sediment is there, except is very low flow periods, we can see this, always the sediment is there, and that sediment concentrations, it increase exponentially when we commit a larger flood or events. So the mostly we try to understand it, how these fluid sediment mixtures are happening it. Like the last class I discussed it, again I am repeating it, that if you talk about the sediment concentrations, which is a very simple concept, that if you take a control volumes, if you have a Bs is the volume of the sediment particles, Bf is volume of the fluid, the total volume of these control volumes will be Bf plus Bs. It's very easy. The sediment concentrations by the volume will be Bs by Bf plus Bs. So as this sediment Bs is increases, the C will going to increase it. That's very basic things. Most of the times we are not doing the volumetric levels, we do the analysis at mass conservation equations, momentum equations, energy equations. So we always linked with the mass, not with the volumetric. So if I find out what is the C, the concentrations by mass, which we denoted as a small c, that's what will be the mass component of the sediment particles divided by the total mass of these systems, which is very easy, just to multiply the particular respective density. Like a rho s stands for here the density of the sediment particles, rho stands for here the density of the water. So you can compute it, what could be the sediment concentration by mass. That means if this C stands for by mass, how much of mass of the sediment concentrations happens is that what we do it per unit volumes, and if you substitute to capital C, then you can get it in terms of this. So many of the times, please don't confuse it whether it is a C in terms of volume or the mass. So you can convert it. If this volume level is data is given it, you have to convert it to the mass level, or reverse, vice versa. You can do it. It is a very simple calculations what we do it to find out what will be the concentration. As I said it, when you talk about the fluid and the sediment mixtures, so what will be the density? We can find out mass per unit volume for that mixtures will be the sum of liquid part and also the sediment part. That's all. The mass is the sum of the mass of the water part and the sediment particles part. That's what you can see it. The same way we can get it, what will be the specific weight of the fluid and the sediment mixtures. Again I am talking, it is a fluid sediment mixtures. You try to understand that, so you can have this. Now if you look at that, many of the times when you talk about the fluid mechanics flow, we always talk about Newton's laws of viscosities. That is the Newtonian fluids. What is there? It's a relationship between shear stress and the shear strain rate. That is what the relationship with dynamic viscosity. Here, because we use the fluid and sediment mixtures, the dynamic viscosity will not be that exactly what is the water dynamic viscosity. So that's what is from experimental data quite clearly establishes that the fluid and sediment mixtures will have a functions of dynamic viscosity of the waters and the corrections factors for the sediment concentrations. C is in terms of the volumetric sediment concentrations. The fluid is mixed with the sediment particles. You can just try to understand. So as I increase the sediment concentrations, there will be more viscosity will come it. That's what is these corrections factors is Standish paper. These are all more than 1 values. So that's the correction factors. If I consider the fluid sediment mixtures, if I know the C value, I can compute it what will be the dynamic, the viscosity of the water and the sediment mixtures, which is necessary for us. Or we can have another empirical equations also developed from experimental data, which is as these power functions. So these are well documented, the experimental finding, the relationship between the shear stress and shear strain rate, assuming it's a Newtonian fluid behaviors. We can find out what will be the dynamic viscosity of the water and sediment mixture particles, which is from the experimental data. Now let me go it very simple examples to say it how we can compute it. Very simple examples that we consider a volume of 2×10⁻³ meter cube of river waters, evaporated it to collect the suspended sediment concentrations which will weight of these ones. Then you have the D50 value, you have a S specific gravity value of that. Then you try to compute it what will be the C value, that is the sediment concentrations by volume, sediment concentrations by mass. Then you want to find out mass density, the specific weight of this and the dynamic viscosity of the fluid sediment mixtures, and if the mu for the clear water is given. So these are very simple problems, just to apply the formulas what we discussed earlier, and only the basic difference is that from the specific weight we can find out the Vs value, we know this Vf value, then we can compute this capital C, small c. Same way if I apply it, I can get it the density of fluid and sediment mixtures. That's what will be much higher than, as I know it, the water density is 1000 kg per meter cube. Because of resistance of the sediment mixtures, we have the density of this water and sediment mixtures is more than 1000 kg per meter cube, which comes out to here 1165 kg per meter cube. Same way you can compute it what will be the dynamic viscosity. Just substitute the C value and mu is known to us. You can see that it is more value, mu m is more higher value than the clear waters because of the presence of the sediment concentrations factors. It's a simple examples to just to demonstrate it how we can compute it if we know the sediment concentrations. You go to the river, collect the suspended water samples, evaporates back, weigh the whatever the evaporated suspended sediment concentrations, then you can do this type of calculations to find out what will be the dynamic viscosity, what could be the specific weight of the sediment particles, sediment concentrations by volume and mass. We can do easily. Just go to the river, collect the water samples, do the evaporations and find out what is the remaining solid particles, which is the sediment particles is there. You just take the weight and find out all these the fluid sediment properties. That's the basic things. So now let's go for next slides. Again I am coming back to the river. Okay, so Brahmaputra rivers, if you look at that, what I just have given the introductions to you, we are having a fortunate to having collaborations with these organizations, which is Inland Waterways Authority of India, to do a extensive river surveys of these big river systems of 10 km wide. I present that data to you, which is quite interesting data to you, that if you go to river, like this type of river of 10 kilometer reach of the river, we cannot do a simple surveys. We need to have a survey vessels equipped with global positioning systems. You know about that. Everywhere you have now the global positioning systems equipped with ADCP, acoustic Doppler current profilers, which measure the three-dimensional velocity components. It measures the depth, it measures the suspended sediment concentrations. More details you can browse through any of the literatures. You can see that what is the ADCP, how to use the ADCP. When you use these type of survey vessels equipped with GPS, equipped with ADCP, with echo sounders, to do a survey transect of these width of the more than 10 kilometers, it takes more than 5 hours. Okay, so it's not that easy jobs. Okay, to do a survey in the river like this Brahmaputra when you have a 10 kilometer. Let me present the data, how complex the rivers. Okay, we cannot simplify the river as we use it. That's what I am to introduce to you. This is the raw data, what we got in the fields. It's not any generated data. This is a major data, the field measure data, Brahmaputra level data. If you look at that, if I plot these three velocity components, one is the primary velocity component, which is a longitudinal directions. There is a vertical velocity component and there is a horizontal, the perpendicular to that. If this is the cross sections, this width can be something like the few kilometers, and these colors are representing my different velocities. If you look at this red color zones, is representing us about 2 meters per seconds. Just again I am repeating it. So if you look at the score zone, the velocity is about 2 meters per seconds, but there are the reaches part where they have a velocity lesser than the 0.3 meter per second, 1 feet per second. But there are the reach where you can have the velocity is more than 2 meters per seconds. That means the velocity variations is there from 0.3 to 2 meters, almost 10 times. Within these cross sections there is a velocity difference, and this is a natural reverse. You can see the velocity difference, how it shows it. That's what is the primary direction. But what it happens is, if you look at these velocity vectors, what you have given it at these directions, the perpendicular to the longitudinal directions, you can see these velocity vectors. And from that you can see that there are the large vortex formations are happening. That's what we call the secondary current. You can easily see that. So when you measure this velocity using the ADCP, you can see this velocity variations in a longitudinal directions in a cross section. Similar way, there will be the velocity variations perpendicular to that, and there is a formations of the secondary currents, which is a large vortex formations are there. You can see it from that. If you look at the vertical directions also, which is the velocity is much lesser than that. If you look at these values, it is centimeter per second. It's not that meter per second. This is a meter per second. It's a centimeter per second. The velocities are less in the vertical directions. But interestingly, this is what it gives is there are the vortex formations are there because of the velocity change gradients are there. There the velocity change are there. If you look at the suspended sediment concentrations, which I said it earlier is 400 milligram per liter to go to 20,000 milligram per liter, you see that these regions it gets on average 300 to 400 milligram per liters. But there are stretches you can have a sediment concentrations can go as high as 800 milligram per liter. So you just look the variability. Just look these are original the field survey data which we have. Nobody has in the world these data sets. So if you look at that way, there is a variabilities in a sediment concentration. There is a formations of the secondary current, and there is the variability in a prime velocity, vertical velocity, and the suspended currents. That's the reasons the river is complex, and we try to understand the river from mathematical point of view and physical concept point of view, and also from conducting at the river scale experiments, and that's the strength of the work we should go it. If you look at that same concept, if I go for larger width, in between there could be a sandbar formations. If you look at how these primary velocity variations are there, too complex. It's too complex. How the secondary currents are there. All these suspended concentrations are available. All these are built up with the secondary current and large scale turbulence structures. There are a lot of turbulence structures we can see in the Brahmaputra rivers, and a lot of secondary current formations are there which carry a large flow and sediment mixtures, and which varies from seasons to seasons, the day to day and the month to month. So that's the value, and also varies from year to year. So that's what is the complicities comes it as we change the sediment properties, as we observe at the field levels. That's the strength of these lectures, and hope you could have enjoyed this lecture. If you come to a typical velocity diagrams given in any textbooks of river mechanics, they say it velocity values is a logarithmic distributions, and sediment concentrations from this free surface follow the exponential decay functions. But does it happen for Brahmaputra rivers? No. That's this. Most of the river mechanics books, they consider this variability in terms of velocity distributions, in terms of suspended sediment concentration. One is the velocity distributions with respect to depth, they assume it varies logarithmically from the bottoms to the free surface zones. The suspended sediment concentrations is varies exponentially decayed from the free surface to the bed. But that doesn't happen in river, complex river like Brahmaputra rivers. But anyway, we have to have all this text knowledge and as well as our practical knowledge, that both will combine it you to represent this river mechanics in different way. That is my idea. More details we will talk about this shear stress formations and all when you go to next levels. So let's go to the next one, is the terminal fall velocity of spherical particles. You know it that any particles which falls from a certain height in a atmospheres, it attains the terminal velocity. Beyond that, the solid particle doesn't accelerate it. It attains a terminal velocity. That means that is the positions, like if I have any particles, okay, assuming it is very theoretically a spherical object which is falling in a water column or the atmospheric columns, you will see that it attains a terminal velocity. At that regions there will be no accelerations, velocity remains constant. When it happens when you have a submerged gravity force is equate to the upward drag force. The upward drag force and the submerged gravity force both are equate each other. There are net force acting on this solid particles becomes zero. There is no accelerations. It moves with a terminal velocity, fall velocity, which is Ws. So we are just equating these two forces, the drag forces and submerged gravity forces. As you know it that when you have the particles, when it goes through that, it creates a lot of the vortex phenomena. Okay, the tail and vortex phenomena. Any fluid mechanics books, you can understand it. And these vortex phenomena are responsible for your drag force components, whether the flow is laminar, whether its flow is turbulence. So the drag force is totally depends upon the flow Reynolds numbers. That is the concept. So if you look at that, the particles which is falling in a water bodies, water columns or atmospheric columns, it will have the terminal velocity. Just equating these two forces and the rearrange the terms, you will get it these ones. It's very simple things. Just look at these equations, which is the giving is the terminal flow velocity is a functions of delta. Delta is S minus A, that means specific gravity minus 1. G, D is a diameter of this spherical object, CD is your drag coefficients. So if I know these drag coefficients, if I know this D value, we can find out what will be the falling velocity, terminal velocity of the sediment particles. How long it will take it to reach the bed materials. If it's say falling it without any flow, it's just pre-suspense, how much time it takes it to reach it to bed. That's what to compute it. If I know this terminal flow velocity, I know the length. If I know this velocity, I can compute how much time it takes it. That's very easy things. So if you look at that way, mostly any textbook or any fluid mechanics textbook, you follow it. The CD is given for the spherical objects. A lot of experimental studies done last 3-4 decades to find out what could be the CD values for spherical objects. For the low Reynolds numbers, when the flow is laminars, the CD is a function of the Reynolds numbers, and if a flow is not laminars, you can have a more complex functions which are the approximations to compute the CD. So if you know the CD, coefficient of drag, if you know the flow Reynolds number, you know the CD value, and you can compute what will be the falling velocity. But we talk about the terminal velocity of the sediment particles. Sediment particles are not the spherical shape. For that, what we need to do is a correction factors. The same way, conducting a series of experiment, it has established with the terminal velocities with your P, Q are the coefficient, the N is a exponent value, and the D stars is a depend upon your non-dimensional particles parameters, doesn't have a dimensions, okay, which is dN, delta you know it, S minus G value, and the kinematic viscous square. dN stands for nominal diameters, what we discussed in the previous class. So you can compute what will be the fall velocity. Similar way, from experimental data, if you know these D star values and these coefficients C1, C2, C4, C5, I can also compute. These are experimental data by Dept in 1982. Okay, they are different equations are there, but more or less these results of the equations are not very much. Okay, they are all empirical equations, and the computations of WS doesn't vary much. Okay, that's just to have a simplifications, have a range of value, you will get it, but not much difference. Similar way, even if in 2000s there is Arens has established more lengthy expressions to compute the WS. 2003 again have a considering this non-dimensional particle parameters, okay, non-dimensional terminals fall velocity. So these are all more going for considering this the particle parameters. That's what is developed to compute it, what will be the W. These are non-dimensional levels, and that what is given it here, you to compute it, what will be the terminal fall velocity of sediment particles. Now if you try to look that, as I said it, that I will have more sediment concentrations. Okay, as the monsoons comes, more the flow comes, more sediment supply will come from uplands. So sediment concentrations are never be a constant, it varies it. When you have the higher sediment concentrations, definitely there will be a reductions in the settling particles. Okay, more the drag force will be there. The more the drag force will be there, more the concentration of the sediment particles. That is what we define as hindered settling effect. That's what conducting a series of experiment, it also develop it that you can modify this terminal fall velocity, which will be the for the sediment laden waters, like when you have a mud flow, when you have a flash floods, a lot of sediment concentrations comes it, that time the settling velocity, terminal velocity, what we will consider it, should consider the correction factor for the sediment concentration. more the sediment concentrations, you will have a less this velocity components, more the drag force will commit. That's the reasons we have experimental proof on these equations, which is 1 minus c by n, where is n is empirical exponent component which vary from 4.3 to 2.3, and that's what is Reynolds numbers increases, and C stand for suspended sediment concentrations, and there are the empirical equations 1961 and 1965 by different two functions. Okay, this is in terms of D50 and this is in terms of C only. That's the empirical equations. You can have a series of equations, any of the book, Fluid hydrodynamics books, you can see that a lot of people, they have done a lot of research to find out what could be the terminal velocity of sediment particles when they have a different sediment concentrations. There are things, let's have a simple examples. Okay, a field survey was conducted in Kameng River, is part of Brahmaputra. The sediment particles is 5 mm, and determining the fall velocities. If the relative density is given, G is given to us, and the kinematic viscosity. Just substitute the formulas, then you can get it what will be the Ws value. Here we have assumed the CD value, and we just compute the formulas to show you that go to the field, collect this sediment, and then you can find out what will be the sediment concentrations like particle size, and then you can find out the what will be terminal fall velocity. Before going to finish these lectures, let's talk about how does river flow varies day to day, seasons to seasons, year to year. As the flow varies, sediment concentrations carried by the river also varies from day to day, year to year, and month to month. That variability is there. How do you analyze that? It's very simple analysis. Today I will introduce to you. First, what you do it, we plot a hydrographs. That means the plotting between discharge and the time periods. So you can plot the discharge versus time periods. Here the discharge in the blue colors. You can see that the discharge versus time periods starting from 31st January to 07 March. So just to have a period of data, it's showing it that how you have a data variability is there in a year. There will be low flow zones, there will be high flow zones, and you can see that the daily variations of the discharge, the flow rate, how the daily levels it's varies. The red colors indicate the sediment concentrations data, which is called sediment graph. But very interesting, if you look at that, the sediment concentrations will be gram per liters is given it here, and the discharge is given in these. You can have this plot of flow sediment hydrographs. Like many of the times you go for any medical, you doctors you go for X-ray reports. So similarly, we look at whenever you start any river engineering projects, first we look at how the flow variability is there, how the sediment variability is there. First we draw flow hydrograph, sediment hydrograph, because that what it explains to us, how does it behave. Like for example, if you look at this case, the sediment variabilities and the flow variability, they do not have a relationship. In some period, flow is there, but the sediment variability is not there. There are early period, so there is clear cut the difference you can identify it, or you can understand the river systems if you just plot the flow hydrograph and sediment hydrograph. That's is the basic things like what we call X-ray reports for any patient. We draw first the flow hydrograph and the sediment hydrographs, and we try to analyze that how things are happening it visually. First try to understand it, then we go for a simple flow durations and the sediment durations curve analysis. What do we do it that, as you know from hydrology book, we follow very simple probability constant, that plotting point method concept, where the probability is m by n plus 1, and n is a total number of the data set, m is a ranking. So, any data set you can do descending order, you can rank the data. So, you know the m value is a rank value. More detail you can go to any hydrology book. So, you know the rank value, you know this n value, you can find the probability, the p you can get it. Okay. So, if you have a 365 of daily discharge data, I can always compute this, the rank of the value in terms of rank values n plus 1 value for a particular discharge data. So, I know the p, the probability of occurrence. I know the time period is equal to 1 by p. Okay. The time of occurrence is inversely proportional to the p. So, you know the probability. So, you can draw percentage of time of accidents and the discharge. That is what we call flow duration curve. From the discharge data, we can plot it, that it can have a like this. After conducting this, the flow data analysis, we can develop a full flow duration curve. Similar way, we can develop the sediment duration curve. The sediment data can be sorted out, can be rank it, compute the probability, compute the time periods, and you can have a percentage of time accidents, which goes vary from 0 to 100%, and you have the suspended sediment concentration. Now, if you try to interpret it, what it happens, like for example, there is a 2 years 1983 2004, the flow duration curve is changes it. It says that how the river flows changing it because of anthropogenic activities, because of natural variability, how the year wise the flow variabilities are there. The low flow is increasing, high flow is decreasing. What is happening it at the probability space? That's what we can do when you have the flow duration curve analysis. Same way, we can know it, the sediment duration curve, that between these 2 years 1985 and the 2004, how the things are changing it. So, the simple way we do the analysis, one is the flow sediment hydrograph analysis, flow duration curve analysis, and the sediment duration curve analysis. More details, I think you can follow any of the books of hydrology books, but in a river engineering we cannot go much details as to we go at next level in this. With this, let me I conclude it today lectures, starting with we discuss about the terminal velocity, we discuss about more concept, just trying to revive back to you. We discuss about the secondary current. Just to remember, there is secondary current generations happens in the natural rivers. The suspended sediment concentrations is much more variabilities in a complex river flow. It's not that simple logarithmic or exponential decay functions. We discuss about the flow duration curve and the sediment duration curve, and be remember it, the flow duration curve and sediment duration curve, it has a variability in a time domain as well as it has a variability in the space domain. It varies from one river gauging station to other river gauging station. It also varies from year to year. So, those quantifications we should do it, try to know it, what is happening to the river catchment. The sediment and the flow duration curve, it shows that what is the response is happening it at the catchment cell at that particular point, what is happening it, whether we are doing deforestations, we are doing a lot of dam structures are built it, any anthropogenic effect is that's what it's reflected in flow duration curve and the sediment duration curve. That's, as I said it earlier, it's just an X-ray of any disease, like a doctor's need it. So, we also follow it, flow duration curve and sediment duration curve. With this, let me conclude these lectures, and these are my PhD students who have been helping me to develop some very interesting slides for you. And to conclude that, from I can quote from Laureate Gilfin's letters that a river seems a magic thing. Okay, river seems a magic things, a magic and moving living part of the very earth itself. So we should understand the river, it's a magic, and it's enjoyable to understand the river. With this, let I conclude this lecture. Thank you.